catalyst. And there are two ways to think of that. One is if you already know all the various logics and the features, this is a kind of straightforward formalization exercise. But also if you don't know the features, but you have some logical framework literacy, which takes a while, but maybe you're getting there this week, you can actually learn the features just by reading formalization. So that's when we really start to leverage logical frameworks, where we can just use the formalizations as the reference definition of the various language features. So then, with a little bit of practice, they actually become as easy to read, or maybe even easier to read, than the inference systems written on paper. And then this can be a very nice teaching resource to understand the various logics. Yeah?
Understanding features by reading the definitions and variable bindings. Yesterday there was this, the ball multiplier was implemented with a higher order function. What if I want logical variables? That's a communication variable.
Oh, that's all taken care of by the framework. You don't do any of that yourself.
Okay.
So when you're formalizing the feature, you're assuming that the type inference, etc., is being taken care of.
Right, okay.
If you want to declare something parametrically, that can apply to any number of objects, you just use a pi binder on the outside.
So I don't implement unification.
No, never.
Okay, yeah.
Well, no substitution, none of that.
Okay. Sorry if I interrupted.
Oh, no problem. That's not working. Well, I think the focus is wrong. No, I think it's just delayed in the. So, to have a better overview of the various theories that are part of the encodings, I structured them into 4 levels. These 4 levels are just for teaching here, so they have no concrete analog in the actual encodings. It's more like a best practice of how the library is structured, and it helps make sense of the various files. So at the base level, we have the fundamental concepts that we're just saying, okay, we have types, we have propositions, those things. I already showed that at the end of yesterday's lecture. And at the next level, we combine these concepts into our base languages. Remember yesterday I showed you those 5 base languages. And then the actual work can start. Relative to one of the base languages, we formalize features like conjunction, function type, and so on. And then we build the actual logics we're interested in by just combining the features. So, recap of yesterday. Theory of propositions just declares the type of propositions, nothing else. And then if we want proofs as well, we declare a type constructor which gives us the type of proofs for. For typing, there's 3 ways to do it. Untyped, we just have terms. Typed, we at least need the TP, giving us the object level types. And then there's 2 options of how to actually type things: soft and hard types. Here we have the relation between terms and types. Here we have the function from terms to types, which should be read as the LF type of an object carries the object level type in its type. Recap the distinction between hard and soft typing. Most important thing to understand is the difference between function and relation. In practice, many of actual languages are somewhere in between because we really want to combine the advantages. main advantage here is it's so much easier. Typing is decided, but then we get the typing through LF, so we can inherit everything from the logical framework. Unique type inference is the key reason why it's easy. But soft typing is way more flexible, because every term can have multiple types, and we can flexibly change what type a term has. In particular, subtyping is a lot easier with a soft typing approach. We can do subtyping also in the hard typed approach, but then basically we have to cast, because every term has a unique LF type. If we wanted to have the type TMA and the type TMB, we can't do that in LF. We need some explicit casting operator that moves something like this. I have a TMA. I want to turn it into a TMB. I can do that if I have proved that A is a subtype of B. Also, it kind of works, but now we always have these subtyping true complications every time we move from one type to another. Whereas in the soft typing, we don't have to change the representation of the object. It just has multiple types to begin with. Yeah.
Can you do soft typing at compile time?
You have to make the question more precise. Like, we're not really compiling anything here. Maybe what you mean is, can we make the soft typed approach as hard as possible?
Okay.
Something like that. And that's definitely a kind of open problem, or like many people have tried things. We don't have, that's not one best solution. So what I'm kind of thinking of is that, and this is the same as what's done in mathematics. Mathematics is inherently soft typed, like a set can be an element of any number of other sets. But then if you look at mathematical notation and mathematical statements, it always, almost always looks as if there's a hard type system in the background. And when you introduce a function, you always say something like f goes A to B in math. Right? You don't say, oh, f is a set. And by the way, f is an element of the set of functions from A to B. You just do that in one thing. So it looks hard typed, even though it isn't. So it seems like hard typing can be understood as maybe sort of macros or some kind of high-level language that gets compiled into a soft-typed kernel language, something like that. But how to do that in LF is not so easy. Maybe on Thursday I can talk a bit about that. But yeah, so I'm more and more thinking that deep down things tend to be soft-typed, unless you happen to be in a very simple lambda calculus that you can, everything is nicely decidable, and hard typing is just what you want. In those cases, I always, in all the other cases, I assume with soft type, and we're trying to have as much hard typing as possible that the user actually sees and nices. And variance, also a recap. Internal propositions, we're saying propositions are a special case of terms of type bool. Propositions as types. Propositions are a special case of types. So prop equal TP. Here we have prop equal TM bool. And internal types, where the types are a special case of the terms, like TP equal TM. And then we get this higher logic set theory, dependent theory. So it's interesting to see that these different languages already at this primitive level are so different and branching off in different directions. Which is one reason why integrating them later on and translating between them is so difficult. Because already the fundamental conceptual assumptions are so different. And the 5 base languages we're going to look at one-type logic, paradigm first-order logic, soft type, hard type, and then with the two variants I mentioned, soft type with internal types, which gets us to set theory, and hard type with internal propositions, getting us to higher order. And now we just want to formalize the various logical features that we know, each one relative to the base language where it fits. So let's start with, any questions so far? Let's start with propositional logic. Those are the easiest features to do. And we don't really need the distinction of 5 base languages because they all have propositions in one way or another. So we can use one encoding of the propositional connectives that works for all the various base languages. In the example repository, that's all of the folder logic propositional. Dive into that one. So the recipe is always here one theory for the syntax, and then one theory for the proof theory. And naming convention is I always stick an ND at the end for the corresponding proof theory, ND for natural deduction calculus. There should be alternative proof theories if you do a Hilbert calculus, sequent calculus, and so on. But in the atlas, there's a strong focus on ND. That's the best. So syntax of the feature that you have, the constant true, is just true colon prop. And then the natural deduction root is just the true introduction root, which proves true. Falsity, equal to that, the logical function false, and the false elimination means if I can prove false, I have a complete. Again, this is technically not natural deduction anymore. This is not something you would see exactly like that on paper, but it works slightly better because LF is a bit more expressive than the natural deduction calculus on paper is. So we have a very nice multiplying. Negation, just a unary operator on propositions. Usual notation with some precedence. I introduced an abbreviation here, which I use later on occasionally. The double negator formula, but that's just to define the operators are not even here. Proof roots for negation, not introduction. If F leads to a contradiction, we have not F, not elimination. We have not F, then F leads to contradiction. And if you have never seen these encodings before, note that this is basically creating an isomorphism between these two types. So we're basically saying the type of proofs of negation is identified with the type of functions go from F to a contradiction. This is one of the places where in deducti you have the option to do things differently by simply rewriting this type into this one. That way, cutting some of the boilerplate and skipping it. That works because for certain connectives whose introduction and elimination roots can be written as basically an isomorphism between two types. Junction, binary operation of propositions, introduction roots, elimination roots, as usual. For some reason I found it necessary to prove this commutativity here. For example, using that in one of the example proofs. Okay. Conjunction, also as usual. Implication, another one of those connectives that whose roots create an isomorphism between two types. So the proofs of F implies G are basically the same as the functions that go from proofs of F to proofs of G. And importantly, this works because of higher order abstract syntax, because the terms of this function type are exactly the terms of this type with a free variable for terms of this type, which is exactly what it conceptually means to prove G under the assumption that F is. In particular, we can't do induction on this proof here. It's not supposed to be here, those are just hints for the theorem. So equivalence, as usual, if I can go both ways, I have an equivalence. And then if I have the equivalence, I can get one from here. And finally, we can combine all these features if we want intuitionistic propositional logic, syntax, start with propositions, and input all the features. For the proof theory of intuitionistic propositional logic, we do the same thing, just have to include all the proof rules. And then there's a couple of theorems that involve multiple connectors. It's always annoying. Didn't know where to put them if they break the modularity. Technically what I'm supposed to do is have a separate theory for every pair of connectives so that then that theory can hold exactly the theorems that need those two connectives. But some of them are very important, so I put them here. I needed to use them all the time. Then classical propositional logic, the syntax is the same as intuitionistic propositional logic, so we do nothing but this include. But then in the proof theory, we include all of intuitionistic propositional logic and the axiom that makes the language classical. I had hinted at the module for practicality yesterday. Classicality is expressed like this. Going to a contradiction kind of represents negation. Doing it twice and then going back to the original formula is kind of a double negation. And then once we have this axiom of classicality, we can prove the usual equivalent statements about classical logic, like consolidation, double negation, elimination, and indirect proofs. So that was the easy stuff as a warm-up. And there's a file pl.derived. This was just a very straightforward exercise where all kinds of abbreviations are introduced and proved, like a conjunction of 3 objects defined as an abbreviation, and then the corresponding rules, and so on. This is, of course, open-ended. There's always more theorems you can prove. This was just a student's exercise. And I put it in here for you so that you can have some examples of things that can be proved to exercise your understanding. Additionally, one of the limitations of LF, we can't really do a flexory conjunction where we have conjunction that takes a list of arguments. So there are no sequences or lists. That's one of the extensions that we have built inside MMT. We have a variant of LF where you have sequences, so that you can just declare conjunction to take a list of propositions. Then I think I'm going to return to those later, and let's do first order features first. Get a little bit more interesting because we have to do binding. Let's start with the untyped first order. Easiest one, untyped universal quantification. So that's the hello world style higher-elastic syntax binding. Term to prop, meaning a proposition with a free variable for a term, gives us back a proposition eventually. And I don't have to because this is modular, but I found it easier for people to read if all the names are unique, even if they're in different series. So I'm using U as a prefix for the untyped operators. And in the notations, this is a parsing limitation at the moment. I'm using a design where all the untyped operators have this U superscript to tell the parser which is the untyped version. I have to implement a better overloading resolution in the parser to allow omitting those. But it has the benefit that when you're reading the files, you always know which language you're in. So for readers, it actually is an advantage. For authors, it's annoying. So the untyped universal just takes its first argument, which is a function. Since functions are written with square brackets in this syntax, this leads to a very nice looking concrete syntax, where if you want to apply for all, give something like this. And then these brackets are redundant. So it kind of looks like you want it to look with the square brackets representing. Introduction elimination rules. For an arbitrary predicate P, which now must be of this type, if we can prove P of X for every X, then we can prove the universe. Here I'm using the eta contracted form. You could also write it like this. Then it looks more like the usual for all. You should be getting bored now. And now to wake you up, let's just change this into the typed version. So if I want to instead have hard typed universal quantification, what do I have to do? Well, starters, I need a different base logic. I need hard type logic, meaning the one where I now have the TM operator that goes TP to type. Recall I have I'm going TP type and hard typed and the untyped version just has term. So this doesn't work anymore. Now, I first have to take a type argument, an A colon TP. That's the type I'm going to quantify over. And now my variable is a TMA. And then, of course, nothing type checks now. I'm just editing the file. And in the notation, I have to now use the second argument here. That's this function. The first argument can be left implicit because I can infer it from the type. all of the hard type formalizations are in the folder and the file hard type. And now we can compare. For the hard type versions, I use the T as a superscript to distinguish. Then for the proof rules, hard type ones have to take the additional argument for the type we're quantifying over. Then we need to find the TMA instead of just a term. Other than that, it's structurally the same thing. And you can see here how tempting it is to think that, okay, it should be possible to generate one from the other. And as an exercise, you can think about, okay, what would have to do, what kind of algorithm would you have that takes as input an arbitrary extension of type logic and returns a corresponding extension of untyped logic, where whatever occurrence of TMA has to be replaced with term. Okay? Then all of these extra arguments have to be dropped. It kind of works already. You have to tweak the notations because you drop an argument, you have to decrement these indices. And it kind of seems to work. Of course, it's an easy case. If you then try to run this on all kinds of other extensions, you get in trouble. I think for equality, it gets a bit harder. And then there's all kinds of different binders that behave slightly differently, where all kinds of extra cases have to be considered. But the basic idea is as I sketched it, that we can generate one from this. Then next, how do we get from those to the soft typed version? Compare soft typed and hard typed. So we start with soft type logic, of course. I'm using the S and here an R for, there was no upper superscript S in Unicode, really. So let's see. They both have the type that we're quantifying over as an argument. And they both have the predicate. But now, in the hard type case, we take TMA to prop, meaning a proposition binding a variable of TMA. We now need two bindings. One for the X colon term, which is just a variable we're binding, and it doesn't have a type yet because it's soft type. And then one assumption that gives us the typing assumption about the X. Now here, this colon is different from this one. I just found the Unicode character that looks like a colon, and then the syntax highlighting shows in a different color, so that's a totally different symbol, totally different operator. That is the soft typing judgment that I showed you before. It's the relation between term and TP that gives me a proposition. So I assume an arbitrary term X and a proof that X is of type A in the soft typing of my object language. And then I have to return a proposition. And then eventually I get the boundary. Other than that, the rules look very much the same. I just have to see wherever I'm binding one variable here, X colon TMA, now I have to bind two, the X and its typing assumption. So I take an arbitrary variable X and an assumption that X has type A. And then I have to apply E to both of these because my P takes two arguments here. So if I had product types like sigma types, I might be able to just merge these two into a single sigma type. In the absence of that, I just have to duplicate everything. Wherever there was one binding in the hard type setting, there's now two soft types. again, we can intuitively think, yeah, it should be possible to generate one from the other. It's quite reasonable to say, okay, whenever I have a TMA originally, I'm going to split it into two bindings, one for the X and one for its typing assumption. And it kind of should be possible to generate these. But again, the subtleties are even surprising. There is one workshop paper we had where we tried it. So far, I haven't been able to produce theories that actually look as nice as I would write them manually. And since it's not that much work to write them manually, for now I'm doing that. Any questions? Yeah?
Yeah, the untyped version and the U for all. It looks like after the notation there's a different notation with two arguments. And
Yes, I was going to delete those before showing them.
Oh, okay. Same for the existence.
Sometimes I use a different notation for printing than for parsing. Because for printing, I can leverage like two-dimensional notations in HTML. And there's a second notation that's with two hashes. That's the one that's going to be used when rendering the term in an environment that can do superscripts, subscripts, and other questions. There's one question that you should have, and that is regarding this assumption. Why do we need that? Or we omit that? So the subtlety here is, so we definitely need it in the proofs, because this assumption here tells us what the type of X is. It has the status of a proof. Of course, we're going to need that to build our proofs in the end. But here we're in the syntax, and the only thing we're building is a proposition. And inside the proposition, we normally can't have proofs anyway. So arguably, there is no way to ever actually use this argument to build the result here. That's because in a soft-type syntax, you just write down the proposition, and whether or not it's well-typed is checked separately. The assumption doesn't help at all. So you could just do this. And indeed, that is a subtle difference between soft-typed languages. So you could have a variant of soft-typed features where in the syntax, the typing assumption isn't provided. It's more systematic to do it this way. And it is more, in a way, future-proof. Because this is something I'm going to talk about later. It is possible to have extensions where we can use proofs inside propositions. I call that proof-carrying terms. That's like when inside a term you carry some proofs to make sure that you can only build the well-typed terms. And then there may be extensions where it is possible to use this. So that's a very typical problem in modular language design. Usually when you start with a simple language, you can radically simplify your ontology and then end up with formalizations that are structurally different from what you need when you generalize. So maybe one thing you already know is the difference between simple type theory and dependent type theory. In a way, simple type theory also has a pi. It's just that in simple type theory, there is no way to ever use a variable in a type, because you don't have any types that contain terms. So it kind of doesn't matter if you have a pi or an arrow, because the only thing you can ever use is the arrow. But if you put the pi in from the beginning, you can then later generalize your language. Maybe you're extending it, and then suddenly you are able to use the variable in a type. And then if you started with a pi from the beginning, your encoding works. Otherwise, if you formalize simple function types with just the arrow, later on some other feature allows you to be dependent, then you have to cut out the arrow, replace it with a pi, which makes modularity a bit more difficult. Like adding stuff is easy, but removing stuff is tricky. So if you already have the arrow, removing it to replace it with a pi is complicated. It's much easier if you have the pi from the beginning. It just happens to be ineffective because there is no other language feature around that allows creating a dependent type. Similarly here, in the simplest soft type languages, it's impossible to actually use this assumption. So you might as well drop it. But then if you later on add other language features that might be able to use a proof inside a proposition, it's good to have this from the start. So now, the same thing for the existential. Very systematically similar. Untyped existential, soft typed existential, soft typed existential. I'm going to skip over that because it is really systematically doing the same thing. Instead, let's look at something new. So we can, again, intuitionistic first order logic uses universal and existential quantification. We have intuitionistic first order logic with equality, which additionally gives us the untyped equality. Untyped equality I haven't shown you yet. Like this, untyped term to term prop in its soft type version. We take the type at which we're comparing two terms and then our two terms, and we return a proposition. And in the hard type version, we take the type at which we're comparing two TMAs and return it. And what I want to show you next is the description operators, which are a different kind of binding. What we know about choice and description? No one? Okay, so I call them often the and the sum operator. They're like zx such that x squared is 25, gives us a 5. Or sum x such that x is greater than 0. So whenever you're picking some object by describing a property, then you have a description or a choice operator. The main difference is the description operator requires unique existence of the object you're describing, like the unique x which has property p. And the choice operator doesn't, it just requires some existence, meaning some x which has property p. And if there's multiple, give me any one of them. So one way to formalize them is like this. So I take the predicate p, which is term to prop. I take a proof of unique existence. So this is now the untyped unique existence binder. And then I get a term. And the semantics is this term actually has the property P, meaning it's the unique value which satisfies the predicate P, and because we have this second argument here which requires us to actually prove unique existence of the predicate, we're making sure that we're only applying the description operator if actually applicable. Choice is systematically the same, except we don't have unique existence. So we just say I have to prove that some x with the property P exists, and then I can get a term representing that x. So these description operators are coming right after the quantifiers, and they're, because that's really how important they are. Maybe you have heard that mathematics is all first order logic based on set theory. And if you actually start formalizing, you realize that's not technically true. Because the set theory is indeed a first order theory. It just has the element predicate, then a couple of axioms about it. But then you realize you have no terms whatsoever. Because if the only symbol you have is the element symbol, which gives a predicate, gives you a new proposition, you never have any function symbols to actually build terms. And that doesn't reflect actual mathematical practice, where of course function symbols are introduced all the time. And it turns out what mathematics technically uses as its foundational logic is first order logic with a description operator. It's just that the mathematicians don't care enough about spelling out the logic to actually make that precise. So if we want to formalize, for example, set theory for logic, we're actually using in the atlas is going to be first order logic plus this description. And then we can define things like the unordered pair of two elements is the unique set that contains those two elements. Yeah.
There are like two numbers after the and sum. Does it mean there is either one or two parameters if we should provide P explicitly, or?
So the first argument and the second just in a row.
Oh, okay.
Except, I mean, this is supposed to be implicit, of course. This is just a proof obligation. You would really want to just give the first argument, that, followed by the predicate. And then the system is supposed to start a theorem prover, actually proves the unique existence, and then fill in this term automatically. Except because finding that is undecidable, the logical framework level, it's kind of hard to do that. So officially in the internal syntax, this takes a second argument. If you were actually to build like optimized implementations, you should make the second argument implicit and get it from a theorem. But yeah, for the manually writing all the stuff, we have to do it ourselves. That's why there's a second. So these two come actually in two variants each. So we remove this. This is the choice from before. And here I have a variant of it. Let's compare this more side by side. this variant is what I call total choice. And the safe choice. The difference is here, when I'm applying the operator, I have to actually pass the proof of existence so that I'm guaranteed that I can only ever apply the choice operator if this predicate is actually satisfiable. This is an unsafe variant where I can apply the choice operator to any predicate I want, including the predicate of fault that's unsatisfied. I can do something like any x such that false. This seems like something you should never allow the user to write, because obviously this term cannot exist. You can't have an x with some unsatisfiable property. So intuitively, I would think this is a mistake. We shouldn't have that. But turns out this is actually the choice operator that you need for high order logic systems. So if you want to formalize the high order logic underlying standard proof assistant, or the one of going back all the way to church, you actually need this one. There's a reason why that exists, because there's a trade-off between these two. Obviously, we have to check this existence at some point to make sure we're not inconsistent in our logic. This variant requires a proof of existence when we apply the operator. The other variant requires the proof of existence when we want to reason with the object. Here we're saying the object constructed by the choice operator always has property P. Here we're saying if some object exists with property P, then the choice operator gives me an object that has the property. So in the case where no object exists, where this is not provable, we can still construct this term, except we can't prove anything about it because this axiom can't be used. So basically we're saying if this predicate is unsatisfiable, I'm getting something back, but it's unspecified what it is. I don't know anything about it, so it's basically useless. So it's, in a way, it's just a trade-off between when we check the proof obligation. Do we check it when we construct the term, or do we check it when we work with it? This is arguably cleaner because it guarantees that we're only building terms that actually are meaningful. But this has the huge advantage of not requiring any proofs inside my terms. So this is what I meant earlier when I said proof carrying terms. Here I'm building a term and it has a proof inside it. And that's something that ontologically many languages want to avoid. It gets more complicated if there are proofs inside our syntax. And that's in particular why higher order logic doesn't do it. That's why higher logic typically chooses this one. It's totally can be applied to any predicate, no proofs in our terms. Then you pay for it by having to do this extra reasoning later on. In practice, it doesn't make a difference, but when you do the logic design, actually is quite interesting difference. So this leads me to two, I call them special features that we can mix into logics that are related to this issue. One, we have these proofs occurring in our terms now. And the other one is we need to be able to return any term, even if the predicate is false. Let's start with the second one. So if this predicate is unsatisfiable, we're returning any term. The hidden assumption here is that some terms exist. If the universe happens to be empty, then this would be inconsistent. Or in other words, this is accepting this kind of choice operator is implicitly axiomatizing our universe to be non-empty. Because if it were empty, then by constructing this term, we proved it's not empty, so we have found the foundation. So this choice operator only works if the universe is non-empty. So making the universe non-empty has an interesting history. So the way I've pieced it together is as follows. So originally, first order logic was built untyped logic, and they required the non-empty universe. Then that was generalized to hard-typed languages, like typed versions of first order logic and then eventually higher order logic. And they just inherited this design choice that types should be non-empty. Types being non-empty has some consequences. It means, for example, that for all x, p of x implies exists x, p of x, which is a rule that is sound if and only if your types are guaranteed to be non-empty. But as we are developing more and more complex type series, the idea that types should be non-empty is increasingly weird. In particular, if we're in dependent type theory, it's not only normal, but in fact desirable to have the empty type. But if we have the empty type, then this would get us into problems. Then we could just say, oh, give me any x of the empty type that satisfies false. Or for that matter, any x of the empty type that satisfies true. That would also be a contradiction. So we don't really want that assumption in general. So why do we even have it in the first place? And I now see it as a bug. So the first order quantifier rules are usually written like this. On paper, we've proved for all x f of x, and for a fresh variable we get f of y. And this thing, introducing a fresh variable, that's technically only sound if your universe is non-empty. If you have the empty universe, you can't just drop a fresh variable of that type because it violates the condition that it's empty. So it turns out this dropping a fresh variable is sound if and only if the universe is guaranteed to be non-empty. And now what the pioneers did when they built first order logic is, instead of fixing the proof rule, they fixed the model theory and just excluded the empty model in the official definition of first order logic. And this is how first order logic is taught nowadays in textbooks, that the universe of the model has to be a non-empty set. And then this rule is exactly what you need to be sound and complete. In LF, it's not even possible to write that rule because LF tracks the context for us, and we're not allowed to simply invent a fresh variable. So the direct representation of the first order elimination of the universal elimination rule is inventing a fresh variable doesn't even work in LF. So if we actually write the universal quantifier rules in the way I've shown you, we end up with rules that are sound even if the universe is empty. Because the only way to eliminate here is by providing a term x, and because I'm providing it, it must already be well formed. Means I already know the universe is not empty because I already have a term for it. I'm not creating a fresh variable out of thin air. The user has to supply the term x for which we're eliminating. So these rules ultimately lead to a variant of first order logic where the universe is allowed to be empty. That's why if we want to formalize actual first order logic as it is done in textbooks, we need one additional module to force the universe to be non-empty. So this says if you want to prove C, you can also just drop a fresh variable and then prove C. And that is equivalent to requiring the universe to be non-empty. So, because LF forces us to be very precise about the context and tracking well-formedness of terms and which variables can occur in which terms, we actually need one more rule than is written on paper to get this effect that the universe is non-empty. But actually, most of the formalizations I'm doing, I'm deliberately not including that module. That way I get a logic where the universe is allowed to be empty, which is usually the one that's better behaved. So this can be done both for the untyped and the hard type, and even for the soft type settings. So there is corresponding modules to say hard types are all non-empty, or in a soft type version that soft types should be all non-empty. And the hard type version of everything non-empty is how the whole systems do it. And that's why the whole systems are able to use this simpler choice operator that requires a non-empty types everywhere. Interesting, in the soft type setting, where every type is a predicate, arguably it doesn't make sense to require every type to be non-empty. But interestingly, that's what Misa is doing. Maybe a design flaw in Misa. But Andre Tribolets explained it to me, saying that forcing the users to prove that all the types are non-empty is a good exercise. Okay, so that is the feature of non-empty types. Which we have to import as well if we want to get standard first order logic. And the other thing I mentioned is proof carrying terms. So that's connected to the issue of proof irrelevance. Ultimately, proof irrelevance is about the question, are the proofs data or just certificates? If the proofs are data, then it matters how we prove something. Different proofs could carry different meanings. If the proofs are just certificates, then it's more like a Boolean question. We have a proof or we don't. And it doesn't matter which proof we have. So that gets us to proof irrelevance, where we're basically saying, well, all proofs are the same. We don't need to distinguish equality of proof. And most of the time, the distinction between proof relevance and proof irrelevance doesn't really matter that much. There are some people who really want to use the proofs as data, and they can happily do that. If you don't care about the proofs as data, you just don't have to worry about it. But you really have to make a decision when you do proof carrying terms, where you have proofs occurring inside your terms. As we have seen with the safe version of the choice operator, when I apply the choice operator, my second argument is a proof. So I can apply it differently with two different proofs. I could have some x term such that, say x greater than 0 and some proof q1, and I could do same with some proof q2. And now these are supposed to be equal, of course. It shouldn't matter how I prove the existence. This is having the role of a certificate simply. Just saying, yes, you're safe, such a proof exists, such an object exists, you can choose one of them. So these two should be equal, which means we need to track this in the equality rules to make sure that these two terms are in fact equal, meaning we have to ignore all the proofs when comparing terms for equality.
Question?
Yeah.
So you are modeling proof irrelevance by quotienting all the proofs, saying they're all the same. But there is the other version, like the S prop in Talk and ACTA, where you actually throw away the proofs and you don't keep them around. Can you do that as well?
That would be nice, yeah. That's like saying, this is like a guard. You can only apply the function if this is true, but then after you've applied it, you can throw the proof away, yeah. That would be nice.
So that would be a kind of an extension of LF, right?
Yeah, exactly. It's a kind of like a guarded function application where you can only apply the function if you satisfy some condition.
Do you know of any work? Like, has anyone done that?
Well, I have. It's just I keep getting stuck because then things get undecidable when you're type checking. Yeah, I don't have any solutions. I've asked people about it. Nobody has good.
I'm asking people about it too. Yeah.
Yeah. It comes up in multiple places, especially if you have refinement types, which kind of behaves the same. And together with dependent types, you very quickly get into very hot water, where even certain meta theorems that are intuitively obviously true don't hold anymore, because you can like squeeze in these partial functions through the backdoor. But yeah, no solution.
Thank you.
Yeah, so once any of our language features allows us to use proofs while constructing our terms, then we have to go back to our soft type quantification and really dig in these assumptions, which I pointed out as potentially redundant earlier. Because now, this proposition could contain some terms, and those terms could apply the choice operator, and then that choice operator might need to prove existence of a term of that predicate, and then that proof might need to make use of these. So, how can we represent proof irrelevance in LF? We could have an equality predicate on proofs, but then we have to carry that through all the time. That gets quite annoying. So in MMT, I can write one extension of LF where I'm once and for all quotienting out all the proofs. So the actual code looks like this. There's some boilerplate around here, but basically what the user has to write is just this one line. P is the global identifier of the choice operator in this case. Of the det operator, which gives me the type of proofs. Then this is the rule that MMT will call every time it has to compare two expressions for equality with type. is constructed with this identifier. So this would be the dead. And then all we have to do is return true to say, yeah, they're equal. We don't even need to inspect the terms at all. They're both proofs. So they're equal. So if the user wants to make things proof irrelevant, they just have to import this one rule. This concretely then looks like this. The proof irrelevance module can be mixed into any logic. We use the term irrelevance rule for the type constructed dead. And this rule, as implemented in the plugin, it says whenever the type checker needs to check equality at this type, it just returns true immediately. So that goes beyond plain LF, so we need an extra rule here which gets injected into the type checker.
The type signature was option of rule, so I was wondering what's.
Oh yeah, because the way it's implemented, things can be undecided. So if you don't know, you have to return that, and then you can return definitely false and definitely. But yeah, so the implementation, I didn't simplify it. There's a whole bunch of stuff in there to track the general case, error reporting and all these. But conceptually, really, it's just one line to return. So classical logic I've already shown you. So that gives me, this gives me 3 special mix-ins: classical, non-empty types, and proof irrelevance. So if I take all of these 3, plus all the propositional connectives, plus the quantifiers, I get standard first order logic, as it is usually seen in textbooks. And then if I also add one of the description operator versions, either the safe or the unsafe one, then I get the version of first order logic that is implicitly assumed by mathematicians as a foundation of sense. So those are kind of the basic features to get started with first. Then let's look at higher order logic. Interestingly, there isn't that much of a difference between higher order logic and first order logic when you formalize it systematically here. The main difference is that in higher order logic you add function types. But if you have typed first order logic, you already have equality at every type, quantifiers at every type. The only thing that higher order logic really adds is that it additionally can build functions. But the formalization of equality, quantifiers, and so on is completely agnostic in what types are around. They all just take some type argument. It's universal quantifier just takes one type as an argument. In first order logic, that type is usually just a base type, but the LF encoding doesn't care about that at all. So if you go to higher order logic, all you have to do is take type equality as a starting logic and then add simple functions. And you can build higher order logic. But once you have function types, your equality can just be a constant of type a to bool. This is now the simple function type arrow that we have imported here. I haven't shown you that, but it's the module of simple function types. And then I can quickly build my higher order logic in the same way as for first order logic. I have the intuitionistic variant, the classical variant, and there's a couple options. Do I have eta? Do I have extensionality and so on? So there's a small graph of features of different versions of higher order logic, depending on which things we built in. If I have a choice operator, then I can prove classicality from that. I can prove non-emptiness from that, so I can reorganize the features based on which features implies which other feature. And then let's look at types theoretical features next. I already mentioned simple function types. We'll get to that. But let's start with something easier like unit types and product types. Those again, we need them for the hard and the soft type scenario. The unit type, we start with a hard type language, and we just declare, we have the unit type P, we have the unit term of that type. And the rest are a couple of lemmas you can prove about the unit type. Bunch of. Product types gets more interesting. Now we have to differentiate different versions for soft versus hard typed and simple versus definitively typed. So first we have the simple product types and dependent product types where the second argument may use the variable of the first one, usually written with a sigma versus a product. I realized the simple version to express that simple product types are a special case of dependent product types. Now, if I have dependent product types, I can just define the simple product types as a special case where the second argument doesn't use the variable x. So this gives me just the types. I still need the constants for it. So for simple products, I import the simple product types, and then I have simple pairing, simple first projection, and simple second projection. For the TMA and the TMA, I get the term of the pair. If I have the term of the pair, I can do the first projection to get the A, or the second projection to get B. As the usual conversion rules, if I have a pair of A and B, I take the first component, I get an A. Second component, I get the B. Here using comma to write the pairs and subscript 1 and 2 to write the projections. And again, I have the superscript T everywhere to indicate we're in the typed setting. Things I was going to move. Developing registering these things as rewrite rules. And then similarly, we can do dependent products. Oh. Dependent pair looks systematically similar to the simple pair, except we can use the value of the first argument and the second. Projections again look very similar. That's for the hard type setting. In the soft type setting, we can import the types from before. I wanted to show you the difference between hard type and soft type dependent products. So again, the TMA, we have a term here. And we need to track types first variable. And again, we have the option whether we second assumption for the type of that or not. We want to, we do it like this. So you don't need to understand the details of every one of those. The more interesting thing is I want to give you an overview of how many different variants we have. So we have the quantifiers, at least universal existential and unique existential, so 3. But we need every one of them for untype, hard type, and soft type. So 3 by 3, so you have 9 qualifiers already. Then we have choice and description. So indefinite requiring just existence, and definite requiring unique existence gives us 2, choice and description. But then everyone comes in these 2 variants, which are called the safe and the unsafe one, depending on when we check the proof obligation. So that's 4. And then those we have, again, for type, untyped, hard type, soft type, so 12 of these description choice operators. Non-emptiness, we only need 3 times, once for untyped, once for hard type, one for soft type. And now for product types, we need them for the simple and the dependently typed version. And then we need those for the hard and the soft type case, so it's 4. And then, as I just said, if we want to have this additional variant reflected that you can require this assumption or not, then we have 6. So very quickly, the amount of modules explodes if you systematically write them all. And that's already under the conscious limitation of these 5 base languages I showed you initially. If we want to add, say, different universe hierarchies, then everything again acquires 1 more dimension. So then we have a handful of different ways to formulate universe hierarchies. And then we have for every one of those, all the some 20, 30 modules I have shown today have to be multiplied for every different way of doing universe hierarchy. That's the reason why universes are deprioritized so far in the atlas. Not because it's like fundamentally difficult or impossible to formalize languages with complex universes, but simply because the amount of modules that we end up writing explodes, especially as the people who work with universes are coming up with subtly different ways of doing universes all the time. So it's not like you have to formalize them once and you're done, but it's like the universe hierarchy of Agda is slightly different from the one of Cork or of something. And then, yeah, you want to capture the historical progression of what Cork used to do and what Cork does now, and then in predicative properties kind of thing. So it's a whole atlas of different ways to the universes, which I've so far shied away from, especially as it is also slightly more difficult to encode, and it would explode as the address. Let's see. The examples I've listed here go far beyond what we have time to cover. Maybe it's good to look at some predicate subtypes. That's one of the features that works well only for soft type languages. So here I can say, well, I have a type, and the unary predicate on that type gives me a new type, notation with a vertical bar like the comprehension operator in set theory. That gives me the option to have a refinement type or a predicate subtype where I get the subtype of a type given by a predicate. And then if I have an X which is of type A and that satisfies the predicate P, then it's also of the type A bar P. elimination rule. This is a subtyping. If something has type A bar P, it also has type A. So here you see how the soft typing allows you to move from this type to this type without changing the representation. The X stays the same. I'm just saying the X has multiple types. It has type A bar P and type A. The corresponding hard typed version needs to cast when going from the subtypes. And the other elimination, if something has type A bar P, it satisfies the predicate. Along the same lines, we can do a hard type word. On the same lines, we can do quotient types. I have a type, I have a binary relation on it. I get the quotient type, typed by an equivalence relation. I can do the projection, it gives me the equivalence class of the X going into the quotient. And then we have the usual well-defined reasoning where if we can show that the function returns the same result whenever two objects are in the relation, then I can apply the function also to limit of the equivalent. So this is quickly stressing your logical framework literacy, but that's okay. It's supposed to be a bit of a tour of showing you what's possible. Let's see. Start this. And then tomorrow we will look at the logic translation aspect in the atlas. So I've only shown you how to build the various models needed to get to languages like first order logic and higher order logic and so on. And then the next step is to look at how can we systematically translate from, say, first order logic to higher order logic, or from higher order logic to set theory. So far the atlas is more like a tree. The only relation between modules is the inheritance relation. And with translations, the whole thing becomes a heavily interconnected graph, where in addition to the inheritance links, we have non-trivial translations. Any final questions? We quit 3 minutes early.